Hello, in this video we're going to be starting to think deeper about sets. I'm going to give you a bit of historical context, and we're going to be looking at two paradoxes, so contradictions, things that can't exist, to do with set theory. Why are we doing that? Well, these, on the face of it, these don't look like useful things for you to learn. But by being able to take the concepts you've already got, thinking deeper about them, stretching them to their limit, we are sort of reinforcing your understanding of those foundational concepts, which are going to be useful. So let's start with this guy. This man is Georg Cantor. He is a German mathematician. He was around the late 1800s, turn of the century. And he is considered the pioneer of set theory. It was his work that really started all the stuff we've been learning so far. And here's a really nice quote from him, which sort of summarizes how he thought of sets. So, a set is a many that allows itself to be thought of as a one. And that's really, really nice. That's what we've been learning. We have a lot of elements, a collection, which we can treat as one thing for the purposes of maths. Now, Mr. Cantor also faced a lot of criticism for his theories when they first came about, because there were inconsistencies. And he himself discovered one of these inconsistencies in 1899. He discovered what we now call Cantor's paradox. And we're going to start speaking about that now. So let S be the set of all cardinalities of all possible sets. So we have a set, and we're going to look at every other possible set in the whole world. We're going to look at their sizes. We're going to put all those sizes and put it in one set called S. And then we're going to start thinking about what is the size of S. So how many different cardinalities are there? What is the size of S? And what is the largest element in S? Now we can start by thinking about this, and we're going to think a bit deeper. Let's try and construct S. So what do we know about some basic sets? Well, we know there's at least one set, A, where the cardinality is 1. We've seen examples of sets with only one thing in them before. For example, the set of just Scotland. We also know that the empty set exists, and the size of the empty set is 0. There's no elements in it. So our very first guess for S is that S contains 0 and 1. Now, S itself is a set. It has a size. The size of S is 2. So if S itself is a set, the size of S is 2. 2 is a valid cardinality for a set. We can put that in S. So now S contains 0, 1, 2, and the size of S is 3. And again, S is a valid set. We can put the cardinality of S in S. And so on, and so on. So you can see that as we start constructing it S like this, S starts to grow and grow and grow, bigger and bigger and bigger and bigger. But more importantly, the size of S is always in S. So this is a set that always grows. There is no end. And also, what's the biggest value in S? What's the maximum value in S? Well, it's the last thing we put in, but the set S is always one more than it. So it doesn't make sense. This setup is a contradiction. This setup doesn't follow the rules of set theory. And this caused a lot of problems for Cantor. It caused Cantor to start thinking about infinities and infinite sets, which we've briefly touched on before. Before we go into that, we've seen infinite sets before. Infinite sets can exist. We've talked about them before, but even before this module, I'm sure you've seen some before. So these are some famous infinite sets. So this sort of boldface N denotes the set of all natural numbers. The natural numbers are the counting numbers, so 1, 2, 3, 4, and so on. There's an infinite amount of them. The boldface Z denotes the set of integers. The integers are the whole numbers, so they are all the natural numbers plus 0, minus 1, minus 2, minus 3, and so on. The boldface Q denotes the set of all rational numbers. They're all numbers that can be written as a fraction. And you would have learned in last module that there are some numbers, again, that can exist but cannot be written as a fraction. For example, pi. So this boldface R denotes the set of all real numbers, which are all the possible fractions and all the numbers that can't be written as fractions, like pi. And they're all the number on the real line. And even further to that, we can talk about the set boldface C, which is the set of all complex numbers, which is the set of all real numbers plus the imaginary numbers, plus when you add imaginary and real numbers together. But you don't need to know about that. What I want to talk about here is all of these are infinite sets, but quite clearly some are bigger than the others. The natural numbers have less elements in them than the set of integers, because the set of integers are the set of natural numbers plus more stuff. Okay, the set of natural numbers is a subset of the set of integers, even though both of those are infinite. So we start to have this idea that there might be different sizes of infinity, and that makes people uncomfortable. Let's have a look deeper. So, which is larger? R plus, which is the set of all positive real numbers, or R, the set of all real numbers? Well, clearly the set of all positive real numbers is a subset of the set of all real numbers. So the set of real numbers is larger than the set of positive real numbers. In fact, it's twice as big. Yeah, it contains all the positive numbers plus the same numbers but the negative versions. It's twice as big. We're happy with that. But now what about this? What is the size of the natural numbers? We've already said there's an infinite amount of them. Okay, we're happy with that. If we let A be the set of all positive even numbers, how big is A? Well, A is every other natural number, so it should be half the size of n. But we can think about this another way. Isn't the positive even numbers just every natural number multiplied by 2? And if so, surely A should be the same size as n? It's all the elements of n, we've just multiplied them by 2. So how can the size of A be both half the size of n and equal to the size of n? And this is something that Georg Cantor spent a lot of time on, and he came up with this idea that all countable sets, well, all countably infinite sets are the same size. Because of what we just did there, we can always relate them back to the natural numbers. We can always put them in an order and go, this is the first thing, second thing, third thing, fourth thing. We can list them off. But with uncountably infinite sets, like the real numbers and the positive real numbers, we can't do that. They are different sizes of infinity. Now, a lot of people, a lot of Cantor's colleagues were uncomfortable with this idea. It still makes some people uncomfortable. And the story goes that Cantor actually went mad by thinking of all these infinities. These days, we don't think that's quite true. He did have a lot of mental illness problems, but that was probably because all his colleagues sort of rejected his work because of these, rather than the work itself driving him ill. I think it was the stress of his colleagues rejecting his work that maybe drove him ill. Move on a couple of years later, and we discover another paradox, another contradiction to Cantor's set theory. In order to understand this, we need to start recapping that, remember, sets can contain sets. So the elements of a set can themselves be sets. So we've introduced us to some sets with some known standard symbols. What is the set of all sets known by standard symbols? right? The elements of this set are themselves sets. I'd like to draw your attention to this Wikipedia article, which is a really cool Wikipedia article. So, as you know, Wikipedia articles are articles of text. Some Wikipedia articles are simply lists of other articles. Okay? And some Wikipedia articles are simply lists of other lists of articles. This Wikipedia article, the list of lists of lists, contains a list of all the lists of lists. But this article itself is a list of lists. So when you actually go onto this, and I encourage you to go onto this Wikipedia article, you will see that the list of lists Wikipedia article is listed in this list. If you think of this as the set of all list of lists, this set is a member of itself. So that leads us to the question, can sets be members of themselves? Let's introduce Bertrand Russell. Bertrand Russell is a Welsh philosopher. He was an aristocrat. His grandfather was actually Prime Minister of Britain under Queen Victoria. And he, as a philosopher, he thought deeply about things and he dabbled a lot in maths, and he looked at Cantor's set theory. Just to mirror what I did with Cantor, I've also put a quote from Bertrand Russell here, and I put this quote in here because it is my favourite quote of all time. Time you enjoy wasting is not wasted time. Nothing to do with set theory, that just makes me feel good about how I spend my time. I like it. But anyway, Bertrand Russell looked at Cantor's set theory and he himself discovered another contradiction to it. And these days, this contradiction is said quite a lot in terms of the Barber paradox. So here's the Barber paradox. In Monmouth, and Monmouth is where Bertrand Russell was born, that's why I chose Monmouth. In Monmouth, all men are clean shaven. Let's take that as fact. In Monmouth, there is one barber. Let's take that as fact. The barber shaves all men and only those men who do not shave themselves. And then we got to ask the question, who shaves the barber? What we've done here is taken the town of Monmouth and split the town into two sets. The set of people shaved by the barber and the set of people who shave themselves. And our setup is you can't be a member of both. They are mutually exclusive. Now, which set does the barber sit? So if the barber is shaved by the barber, then he is the barber, and so he shaves himself. So he must go into the set, they shave themselves. But if the barber shaves himself, then he is shaving the barber. So he must be shaved by the barber. But again, if the barber is shaved by the barber and he is the barber, he must be shaving himself. So he must go in the shave himself set. And so on. We don't know where the barber sits. And so actually the barber doesn't sit anywhere. What this shows is that this situation is a contradiction. This situation cannot exist. Bertrand Russell didn't write it as the Barber paradox. That's a nice visual way of us being able to see it. Bertrand Russell wrote it this way. He said, let R be the set of all sets who do not contain themselves. So if R is in R, then R contains itself. So it cannot be in R. But if R is not in R, then it doesn't contain itself. So by the definition of R, it must be in R, and so on and so on. For context, both of these contradictions, both of these paradoxes, came at a time where there was a big argument in the philosophical and mathematical communities where we were asking, is maths a human-made or natural phenomenon? And the argument was that if it was a natural phenomenon, then all maths could be described by logic alone, by pure reason. And it was thought that Cantor's set theory was the key to cracking this. But what these two paradoxes were shown was that there was a way, using pure reason alone, that contradicted itself, that couldn't exist, which sort of shifted the argument the other direction, was maybe maths is actually a man-made thing and we need to put the rules in there ourselves. People came along later and ironed all these problems out, and the debate still goes on. Is maths, when we do new maths, is it inventing maths or discovering maths? What do you think?